Hi everyone, so this will be me solving PSPM for the session of 2022-2023. Yes, okay, so I'll be setting a 2 hours time limit and we will try to start right now. Okay, so let's try to solve this question here. We are given a diagram which is called figure 1.1, and there are two charges placed at the corner of the right angle triangle as shown in figure 1.1. So there's 8 microcoulomb positive charge and then 5 microcoulomb negative charge over here. They ask you to calculate the magnitude and direction of the electrostatic force acting on the charge of 8 microcoulomb. So this charge, how much force is it experiencing and what is the direction of the force? That's question number 1. Question number 2, the magnitude and direction of the electric field at point P. So this position, what is its electric field? So there are two questions that we need to determine. Let's determine for the first one first. So for the first question, we are asked to determine force. So anything that relates to force and field, we have to be very careful in that we need to consider the direction. Okay, always remember to consider direction when you talk about electric force and electric field. Okay, so make sure to consider direction. Okay, so how do you consider direction? By sketching the electric force diagram or sketching the electric field diagram. So for question number 1, since they're interested in force, we will sketch the electric force diagram. So this is an 8 microcoulomb positive charge. I'm going to call it as Q1. Okay, and this distance over here is 0.100 meter, and this distance here not given, and you have point P over here, and you have this distance here to be negative 5 microcoulomb, which we will be calling it as Q2. Okay, since Q1 is a positive charge and Q2 is a negative charge, if you want to analyze their force, we know that these two charges are opposite charges. So if they are opposite charges, they should attract each other. So you should have forces pointing towards each other. There's force X by 2 on 1 acting by Q2 on Q1. Whereas this force over here will be the force acting by Q1 on Q2. So these two forces here form an action-reaction pair attracting each other. But now they're interested with the electrostatic force acting on the charge 8 microcoulomb, so they're interested with F21 over here. So let's determine the magnitude for F21 followed by its direction. So F21 will be equals to K Q2 Q1 divided by the distance between 2 and 1 squared. Okay, so substitution 9.0 times 10 to the power of 9. Q2 over here, we modulus it already, so we don't want to introduce the sign, the negative sign, we remove it. It's just 5 micro. Q1 over here is 8 micro, so 8.0 times 10 to the power of negative 6. So down here you have your R21. R21 is the distance between 2 and 1. This distance here, we need to find it. It's actually, you can find it through a Pythagoras theorem. Okay, 0.070 meter. Okay, so you can see that you are given the opposite and the adjacent. They are asked to find the hypotenuse. So this one is just a Pythagoras. Okay, so you can do it as 0.100 square plus 0.070 square. You don't need to do the square root because the whole thing here needs to be squared, right? So this is enough already. Okay, so let's determine the answer. .16 Newton. Okay, let me double check. Okay, should be fine. So this is the magnitude. How about the direction? For the direction here, we know that we need to find this angle over here. Okay, this particular angle, we need to find it first. Okay, so let's label it in green. This is the angle theta. So to find this angle, we see that this is the opposite. This is the adjacent. So can do tangent theta is equals to opposite. Opposite is 0.070. Adjacent here is 0.100. So from here you can find theta to be equals to 34.99. So this is equivalent to, yeah, just write 34.99 degree. Okay, so once you have your angle, you have your magnitude already, you should write your final line answer. Your final answer should be force by 2 on 1 equals to 24.16. This one is the magnitude. The direction will be 34.99 degree. Okay, so this one is considered below positive x-axis. Okay, why is it below positive x-axis? Because if you think of x and y axis, this is happening below the x-axis and it's happening on the positive side of the x-axis. That's why it's below positive x-axis. I think if you write towards the negative 5 microcoulomb charge, I think it's also acceptable. Maybe I can write towards the negative 5 microcoulomb charge. Okay, maybe this is acceptable as well. Okay, next question 2. Question 2 asks for the direction and magnitude of the electric field at point P. So point P over here, what is the electric field? So point P here, we have electric field produced by both Q1 and Q2. Okay, when we ask about what is the electric field over here, we need to know who produced the electric field over here. Who produced the electric field over here? Both Q1 and Q2. So Q1 produced its own electric field in its surrounding. So P is at its surrounding. So therefore P will have electric field produced by Q1. Same thing for Q2. Q2 produced an electric field at its surrounding. So P is at the surrounding of Q2. So therefore P will also have electric field produced by Q2. So at point P, there will be an overlap of the electric field produced by Q1 and Q2. And we need to figure out how to combine them together. Remember, you need to consider their direction when you combine. So you cannot just add them up. This is not a simple addition kind of question. Okay, so to deal with this question, you need to know that for electric field, if it's produced by a positive charge, if it's a positive charge that produces electric field, the electric field will have to point away from the positive charge that produced the electric field. Okay, electric field point away from the positive charge that produced the electric field. If it's a negative charge that produces the electric field will have to point towards the negative charge. Okay, so here 8 microcoulomb is a positive charge. So P at point P, there's electric field produced by this 8 microcoulomb charge. Since 8 microcoulomb charge is a positive charge, the electric field need to point away from 8 microcoulomb. How to point away from 8 microcoulomb at point P? Away means that we are pointing downwards. If you are pointing towards, then it's upward, but you are pointing away, so you need to point downwards. So this one will be electric field produced by 1. Okay, we call it Q1 already, right? So this is electric field produced by 1. Next, there's also electric field produced by negative 5 microcoulomb charge. Negative 5 microcoulomb charge is a negative charge. So electric field at point P over here, we need to point towards the negative 5 microcoulomb charge. How to point towards negative 5 microcoulomb charge is to point to the right. This will be electric field produced by 2. Okay, so we need to find a combination of both of this. So you can see that on the x-axis, sum of EX, on x-axis there's only one electric field, which is positive E2. Why do I write positive E2? Because it's E2 and it's pointing in the positive x direction. Okay, so you can continue and calculate it to be positive K Q2 over R2P square, which is 9.0 0 times 10 to the power 9. Q2 is how? Q2 is negative 5 microcoulomb, but we cannot put in the sign because we modulus the Q already. R2P is the distance between Q2 and P. Between Q2 and P, the distance is 0.07. To square it. So our answer will be .184 times 10 to the power of 6 Newton per Coulomb. Okay, how about sum of EY? Okay, if you look at the y-axis, there's only E1, but it's pointing in the negative direction, which is downward, so this is negative E1. Okay, so we can do K Q1 over R1P squared, which is equivalent to negative 9.0 times 10 to the power of 9. Q1 is 8.0 times 10 to the power negative 6. Distance between 1 and P, the distance is 0.1. So we can calculate this. This should be negative 7.20 times 10 to the power of 6 Newton per Coulomb. So once we have both of this ready, we can combine them. We know that if you want to combine the x and y component, we need to do Pythagoras theorem. So sum of EX squared plus sum of EY squared. So sum of EX is 9.184 times 10 to the power of 6 square plus sum of EY is negative 7.20 times 10 to the power of 6 square. Okay. You get 1.167 times 10 to the power of 7 Newton per Coulomb. Okay, double check my answer. Oops, something seems wrong. Okay, seems fine. Okay, so right now direction you can do, theta can be determined using inverse tangent of sum of fy, sum of ey divided by sum of ex. Okay, I don't think there's a lot of space. Ey will be 7.20, we modulus it already, so we don't need to put in the sign. Ex will be 9.184 times 10 to the power of 6. Also don't need to put in the sign. Okay. I'm doing a bit confused. EY divided by EX. Okay, the angle is 38.10 degree. Okay, so once you obtain the angle, you should write your final answer. I don't have the space to write it, I write it somewhere here. So the sum of electric field, you can write at point P also, okay, it's equivalent to 1.167 times 10 to the power 7 Newton per Coulomb. The direction should be 38.10 degree. You can see that EX is positive, so that means by it's to the right. EY is negative, means by it's downward. So if you combine right and downward, you should get the fourth quadrant. So fourth quadrant is below positive x-axis. Okay, so yeah, you need to deduce the direction of the electric field based on EX and EY. EX is to the right because it's positive, EY is downward because it's negative. So right and downward, if you combine, it should be the fourth quadrant, so that's below the positive x-axis. Okay, so that's how you solve this question. Let's move on to the next one. Let's try to solve this question here. Two parallel metal plates A and B, so you have metal plate A and B are connected to a 12-volt battery as shown in figure 1.2. So this is still question 1, so this is chapter 1. If you see a parallel plate, immediately you need to think of it's a uniform electric field being produced in between the plate. Okay, calculate the magnitude of the electric force acted on the positive 4 microcoulomb test charge on the surface of plate B. Okay, so what happened over here is, because you are connecting it to this battery over here, the positive terminal is at the lower, is on the lower side, so it's connected to plate B. So this will be the positive plate. Okay, the negative terminal is connected to plate A, so the plate A will be a negative plate. Okay, so what kind of electric field is being produced? Connecting positive plate to negative plate. Okay, so this is the electric field. This is 2 cm. Then afterward, they say positive 4 microcoulomb test charge on the surface of plate B. So we are going to put a positive 4 microcoulomb test charge on plate B. Okay, so they are asking how much is the force experienced by this particular charge over here. What happened is this positive charge here, it is placed in a uniform electric field, right? So this positive charge here will be interacting with the electric field, and as a result, you experience a force. So this is the question they're asking for. They're asking for the magnitude of the electric force. So you should determine the electric field in between this plate first. Once you determine the electric field, you know that everywhere in between the plate, the electric field is the same. So you can immediately assume that this is the electric field interacted by the positive charge. So once you know the value of the charge, you know the value of the electric field that is interacting with, you can determine the force by using the interact equation. So that's our strategy to go. First, we determine the electric field first. The electric field, if it's uniform electric field, you can use this equation. If it's uniform, immediately you can think of the equation is equal to delta V over D. Okay, delta V is the potential difference across the two plates. That's 12 volt because that is what you connect across the two plates over here, a 12 volt battery. Then distance between them is 2 cm. So 12 volt divided by 2 cm, which is 0.02. From here, you can get your electric field to be equals to 600. So 600 Newton per Coulomb. Okay. So this is the electric field that this particular charge should be interacting with. So if we use the interact equation is E is equals to F over Q, where Q is the charge that is interacting. Okay. the charge is interacting with the electric field. Okay, then this is the electric field that the charge is interacting with. Okay, and this will be the force experienced by the charge. Okay, the charge interact with an electric field, therefore it experiences a force. So everything connects together by this particular equation. We put a modulus for the Q over here because both E and F here are magnitude of electric field and electric force. Since they are both vectors, right, if we find the magnitude, there's supposed to be no direction in the value itself already. The direction is represented by the sign, but we say we don't want to represent the direction, so there should be no sign for E, no sign for F. So we should take both of them to be positive. So if both E and F are positive, that means your Q, no matter what, must be positive. So if it's positive charge or negative charge, you modulus it just to remove the sign for this equation to be logical. So electric field is 600. Okay, the charge is interacting with it is a positive 4 microcoulomb, but we don't want to talk about the sign. We just put in the value, then here you can get your force. So here you can get your answer to be 2.4 times 10 to the power of -3 Newton. So yeah, that's the force experienced by this particular test charge when it is placed at plate B. The question is, if you place it anywhere else in between this region, actually you get the same force as well, because you know that everywhere in between these two regions, in between these two plates, everywhere in this region over here, the electric field is the same. So the electric force that is experienced by the charge will still be the same as well. So it's not necessarily placed at surface of plate B. You can place it in the middle, you can place it at plate A, you will still get the same answer as well. Okay, because everywhere here the electric field is the same. So use this equation, same electric field, same charge, so it will be the same force as our answer. They are not asking for direction, so I will stop here for this question. Next. Let's try to solve this question here. Two fully charged capacitors C1 and C2 are connected in series with a 1 kilo ohm resistor. So these are two capacitors and one resistor, as shown in figure 2. Calculate a time constant when the switch is closed. So they are asking for time constant. Time constant can be determined using tau is equals to RC, but C you have to calculate the C effective lah, or C12. So how do we do C12 over here? We know that the connection is from C1 and C2 in series become C12. Okay. So how do you connect? How do you combine two capacitors that are in series? In series, to combine them, you need to do the inverse of C1 and C2, right? The inverse of C1 add up with the inverse of C2. This process here will allow us to determine C12. So once C1 is 100 mil, C2 is 200 mil. Okay, my answer will be 0.667 times 10 to the power of -6 farad. Okay, double check. Here, if you want to put in fraction, is 1/15,000. Okay. Okay, so you have your C12 already. You can proceed to substitute inside. Your R is 1 kilo, so 1 times 10 to the power of 3, 1 kilo ohm. C12, just now I say is 1/15,000. Okay. So from here I get that my time constant is 1/15 second, which is equivalent to 0.067 second. Okay, so that's it. That's how you determine time constant. Find the effective capacitance or equivalent capacitance first before you use your tau is equals to RC. Next, let's try to solve this question here. We have a parallel plate capacitor which has two plates of area 100 cm square separated by 5 mm connected to 300 volt. They ask for the charge on the capacitor. So if you'd like to illustrate the situation consists of a parallel plate capacitor. Then they tell you that the area of this plate here is 100 cm square, which you can convert into meter square. Okay, how do you do your conversion? You eliminate cm, you introduce meter, right? But remember, there's a square, so you have to square both things as well. So you know that 1 meter is equivalent to 100 cm. That's true, but don't forget the square that you just add on at the back. You square it, right? So your conversion, you also square your conversion. Okay, so if you proceed to do this, you will see that it is equivalent to 0.01 meter square. Okay, so this is the area, then it's separated by 5 mm, so 5 mm is 5.0 times 10 to the power negative 3 meter, and this capacitor here is connected to a 300 volt battery power supply lah. Battery is difficult to have 300 volt. Okay, the power supply that is 300 volt. Okay, so this area here and this distance over here, I believe it will tell you that you can find your capacitance from it. Okay, epsilon A over D, these are the factors affecting capacitance, the cross-sectional area of the plate, not cross-sectional area, the area of the plate and the distance between the two plates. So just make sure you put it in with the correct unit, then you should be fine. This 8.85 times 10 to the power negative 12 is a permittivity of free space. You can obtain it from the constant sheet. The area here is 0.01. Make sure it's in SI unit. The distance between them should be 5 mm, but convert it into SI unit as well. So from here you get your C0 to be equals to 1.77 times 10 to the power of negative 11 farad. So this is your capacitance. Then you know that this capacitance over here is connected to a 300 volt battery or power supply. So you can know that capacitance over here is actually the ratio of the charge to the potential difference across the plate. So you have the capacitance ready. You know the voltage across the two plates is 300 volt because that's the power supply that you're connected to. So from here you can know how much charge is stored inside this capacitor. So the charge stored in this capacitor will be 5.31 times 10 to the power of negative 9 coulomb. Okay. So a fairly straightforward question, even though if you have a problem with the concept, I believe just by seeing what's being given, you are able to deduce everything just by the equation. Okay, so this is the charge stored in the capacitor. Next, question number 3. A current of 2.1 ampere flows through a wire of 6.9 meter long and 0.33 millimeter in diameter. Okay, when you see they give you a length of wire, they give you a diameter, you should imagine that this diameter here leads you to the cross-sectional area of the wire. Okay, so if you have your area, you have your length, you are actually talking about resistance over here. So these two values here will tell you the resistance, and now you have your current and your potential difference. So this is related to Ohm's law, V is equals to IR. So they ask for resistivity, which is something related to those stuff over here. Okay, so let me sketch a situation. So you have your wire. Okay, this wire is 6.9 meter long. And the diameter is 0.33 times 10 to the power of negative 3 meter. Okay, and you're connecting it to a 12 volt potential difference. And right now the current flowing through this circuit over here, the current flowing through is 2.1 ampere. Okay, so if you have your voltage, if you have your current, what you can determine here is the resistance of this particular wire, right? So that's what we do for now. V is equals to IR, so you know that the voltage across this wire here, the voltage across this wire is 12 volt because that's the power supply you're connected to. The current flowing through the whole loop should be the same. Okay, there's only one path for the current to flow, so everywhere it should be 2.1 ampere. So the current flowing through this wire should also be 2.1 ampere. So that's your current. So from here you can find your resistance, and your resistance should be equals to 40 divided by 7 ohm. Let's write in fraction because I need to use this value in other equations later. Okay, now I know that this resistance depends on a few factors, which is the material represented by its resistivity. It depends on its length as well. The greater the length, the greater the resistance. And also the cross-section area. The greater the cross-section area, the lesser the resistance. So this is the equation that shows the three factors that affect resistance. There's also temperature, but it's not contained inside this equation. So right now you have your resistance to be equals to 40 divided by 7. So rho over here is what you want to find. You have your length is 6.9 meter. But your area over here, they are giving a diameter, you have to change it to area. So you know that this is a circular area, so it's pi r squared. But r can be obtained by taking a diameter divided by 2. So 0.33 times 10 to the power negative 3, this is the diameter, divided by 2, you get your radius. But you still remember, your radius need to be squared. Okay? So from here I get my rho to be equals to 7.08 times 10 to the power of negative 8. The unit for resistivity is ohm meter. How to determine it? This one is length, this one is area, meter square. So if you combine them together, you get m negative 1. Okay, this side you have your resistance in ohm. So if you bring it to the other side, if you bring per meter from the right hand side to the left hand side, it will be shifted from m negative 1 to become m, right? So you multiply with ohm, you get ohm meter. Okay, you have to do a bit of deduction. Maybe if you cannot see it, you rearrange the equation to be rho, then it will be RA over L. Okay, RA over L, so this one is ohm, this one is meter square, this one is meter, combine meter square and meter, you get meter, combine ohm and meter, you get ohm meter. Okay, so this is the unit for resistivity. Okay. Yeah, should be fine. So that's it for this question. Next. A dry cell of EMF 1.5 volt is connected in series with a 1 ohm resistor. Determine the cell's internal resistance if the voltage across the terminal is 1.4 volt. Okay, this is a relatively straightforward question. Basically, what happened here is you have a battery, but your battery has internal resistance, so I'm going to block it with resistance as well. So this is my battery. There's resistance inside it, so we call it internal resistance. We know that the EMF is 1.5 volt, but we don't know the internal resistance is how much. But this particular battery is connected in series with a resistor. We place a resistor somewhere over here, and our resistor here has a value resistance of 1 ohm. Okay, so they tell you that if the voltage across the terminal is 1.4 is if you take a voltmeter and you measure the voltage across the terminal of the battery, what you'll be getting here is 1.4 volt. And what's the meaning of this value here? This value here is actually the terminal voltage, because it's voltage across the terminal, right? It's actually terminal voltage, or you can think of it as the voltage available for the external circuit. Okay, so there are a few equations that relates between EMF and terminal voltage and internal resistance. One of it, you can think, there's many, you can think of it as the energy supplied by the battery will be the energy supplied to the external circuit plus what's being consumed in the battery. So this is one equation, and you can change the equation to be EMF is equals to I current flowing through the internal resistance and the resistance outside the power supply. This is also another equation. Okay, then you can also talk about the whole situation in terms of potential divider. Let's say we are interested in what's available for the external circuit. What's available for the external circuit is terminal voltage. It's basically taking what you have. In total, you have 1.5 volt, but it's shared between the internal resistance and the resistance outside the battery. So both of them are sharing this EMF, but if you are interested in what's available for the external, that will be the external resistance, which is the resistance outside the battery. I think for this particular situation, we have all the information to use this third equation using the concept of potential divider. So we know that the voltage across the terminal voltage is 1.5, and it's actually being shared from what 1.4, sorry. This one is 1.4, available for external circuit. That one is terminal voltage. Terminal voltage is 1.4, and it's actually a portion of 1.5 volt that is being shared across R and R. So this is 1.5. 1.5 is being shared between internal resistance and the resistance outside the battery. But what we are interested in is the voltage available for the external circuit, which is the resistance outside the battery. So we put the resistance outside the battery as our resistance of interest. So small r over here we don't know, but the big R over here is 1.0, 1.0. So you have one unknown R left. Okay, so 1.4 divided by 1.5. You get R is equal to 1 over 14, which is equivalent to 0.0714. Okay, let me quickly check whether it's correct or not. Yeah, should be fine. So this is the internal resistance. So you can see that the internal resistance is this much, the external resistance is this much. So the internal resistance will take up a small portion of the 1.5 volt. Then the rest will be given up to the external resistance, which is the resistance outside the battery. Okay, so that's the idea of internal resistance and how it relates to the electromotive force. Next. So you are given this circuit over here, which has 3 resistance, and A1 is the ammeter that measures the current flowing through 10 ohm. A2 is an ammeter that measures the current across 20 ohm. So you have 3 resistors connected to a power supply. They ask you to determine the effective resistance, determine the potential difference across each resistor, and the readings of ammeter A1 and A2. So basically you just find everything, you just combine everything, then reverse everything, then you can find the potential difference across all the resistors. You can find the ammeter, and you can find the current across all the resistors as well. Okay. Oh, they only give you this current, so this is interesting. Okay, so you do combine and reverse as usual, so let's do combine first. Okay, before you do combine, make sure for series and parallel, there's a 4 steps process you need to follow. First, label everything so that everything has a unique name. Next, you rearrange if necessary, but I don't think it's necessary. It's very clear cut how you need to combine here. Number 3, this will be combine. Number 4, you do reverse. Okay, so I'm going to call this as R1. I'm going to call this as, oh no. If they call this A1 and A2, we'll try to follow. Okay, they already tell us that this is A1, this is A2, right? So maybe I'll just call it as R1 so that it matches the subscript better. R1 and R2. So this will be R3. Okay, so I'm going to combine R1 and R2 in parallel first. Afterwards, I'll combine R12 with R3 in series. So the diagram should be something like this. The next diagram, R3 is still here, but you have R12 over here. So this is R3. Don't need to worry too much about the emitter because this is combined. We are just finding effective resistance, so don't need to worry where are the emitters actually. Okay, then if you combine R12 and R3 is in series, you get R123. This is 15 ohm. Okay, so let's find R12 first. R12 is in parallel, so to find R12, you need to do the inverse of R1, add up with the inverse of R2, then you inverse the whole thing back. So R1 is 10, R2 is 20, -1. So this is 20 over 3 ohm. Then next, continue to find R123. R123 is combining R12 and R3 in series. So you just add up R12 plus R3. R12, the value is 20 over 3. R3, the value is 15. Add up, you get 65 over 3 ohm. I write 1 in fraction because that's what I'll be using for substitution, but also provide answer in decimal because that's what usually the examiner wants. Okay, so effective resistance will be question number 1. So I already obtained my effective resistance. Oops. Okay, so that's question number 1 solved. Next, we're asking for potential difference across each resistor. So there are 3 resistors. We need to find V1, we need to find V2, we need to find V3. Then they ask for a reading of ammeters A1 and A2. That one will allow us to determine current across resistance 1, I1, current across resistance 2, I2. So basically all these things can be obtained if you do a reverse process. So let's go through reverse right now. So reverse starting from the rightmost diagram. R1, 2, 3, reverse backward. Again, don't worry too much with where is the ammeter. Again, we just need to know what are they measuring. Okay, then later when we get the value, we will just see that it's a reading of ammeter. We don't need to draw back where is the ammeter. Okay, so this is R3, this is R12, this is R3, this is R1, this is R2. Okay, we don't know the voltage, we just write it as V. So right now we know that R123 is equals to 65 over 3 ohm. We don't know the voltage across the everything. They don't let us know the voltage over here, right? So we just leave it as a blank. So because we don't have the voltage, I don't think we can find the current as well. So current can be obtained by using V over R, right? But because we don't have V, we cannot find I as well. So technically we have missing information over here, but don't worry, just move on to the next diagram. Okay, even though there's missing information, if you find nothing that can be used to fill in these 2 blank over here, move on to the next grid. Okay, for the next diagram, what do? You check what is being splitted to what. R123 is being splitted to R3 and R12. Previously we know that this is combined in series to form R123, right? So we need to recall, for if you're talking about series over here, series, the current should be the same. It should be the voltage that add up. For parallel, it should be the voltage that is the same. It should be the current that is added up. So we are talking about series for R3 and R12 over here. They are connected in series. So for series, I should be equal. So I Which current? 3 and 1, 2. So I3 is equals I12 is equals to the combination of it, I123, which we don't know the value because we leave it blank over here. The voltage should be added up instead, so V3 plus V12, V3 plus V12, not I12, voltage added up. Okay, V12, combination of it is V123, and again we don't know the value for V123. Okay, so for this part, we can say equal and equal, we don't need to find the value because the answer will be at the back over here. But if this is added up, we need to find V3 and V12 because the answer here, even though if we have a value over here, it won't tell us V3, it won't tell us V12. If it's equal, it will be the same, but if it's plus, we need to find it separately. So V3 can be found using I3 multiplied by R3, whereas V12 can be found using V12 is equals to I12 R12. Okay, just make sure when you use Ohm's law, make sure that the substrate is consistent. 3 3 3 1 2 1 2 1 2. Again, I believe you don't have all these values. Actually, you have I3 because I3 here is the current passing through R3, right? Current passing through R3 is actually 0.24, so here is 0.24 ampere. Okay, so you have I3, so you can substitute I3 actually. I3 is 0.24, that's the current passing through R3, and R3 the value over here is 15 ohm. So from here you can find V3. V3 is 3.6 volt. Okay, but V12, do we know the value? We don't know, but we know that we know I3 already, right? So I3 should be equals I12, should be equals I123. I3 the value is 0.24, so we can put 0.24 ampere over here. Okay, so now if you have I12 is also equals to 0.24, so we can calculate 0.24 multiplied by R12. R12, what's the value for R12? 20 over 3. So from here, you should be able to get 0.24 times 20 divided by 3. It will be 1.6. Okay, so if you take V3 plus V12, you add them up, you should get a value of 5.2 volt. Okay, so now if you have V12 already, you can actually move both ways. You can move to the next diagram or you can move to the front diagram. But I think they asked for V1, 2, 3, V1, V2, and V3, I1 and I2, right? So everything should be moving to the right diagram. For the right diagram, only you are able to find it. If you move to the left diagram, you find V1, 2, 3, and I1, 2, 3, which is not what they want. So we move on to the next diagram. For the next diagram, we see that R12 is combined, R12 is split to R1 and R2. And we know that R1 and R2, they are connected in parallel. So for parallel, their voltage is the same. So which resistor is involved? R1 and R2 only. It's only R1 and R2 involved, so we are going to ignore R3 over here. Just consider R1 and R2. Their voltage should be the same. So V1 should be equals to V2, should be equals to V12, should be equals to V12. We have the value is 1.6 volt. The current should be added up for parallel. So current for only the two resistors that are involved from here to here. So R12 split into R1 and R2. R3 is untouched, so we are going to ignore it, just R1 and R2. So I1 should be added up with I2. And it should be equals to I12, which is also equals to I12, we have the value 0.24. Okay, so equal means we don't need to find V1, we don't need to find V2. The answer is just 1.6, but I1 and I2 we do need to find it. That's what the question wants as well. I1 is V1 over R1, just Ohm's law rearrange. V1 the value is 1.6, R1 the value is 10. So from here you get 0.16 ampere. Okay, I2 will be equals to V2 over R2. So V2, the value is also 1.6. R2, the value is 20. So from here, you get 0.08. Okay, so how to double check? We know that if I1 and I2 added up, it will be 0.24. So 0.16 plus 0.08 is indeed 0.24. So it makes sense. I1 and I2, the value do make sense. And actually, this is the answer for question number 3. For question number 2, there's a potential difference across each resistor. So this can be found here. You have V3, and over here V1 and V2 both equals to 1.6. Okay, so let me roughly check the answer. Okay, the current should be the same. So they say the current R3 and R12 should be the same. 0.24 times 15. This is the voltage here. Yeah, everything seems fine. Okay, so I already determined what the question asked for, and it can be determined through this process of label, rearrange, combine, and reverse. When you combine, the purpose is to find effective resistance. When you reverse, make sure your objective is to find V and I for each diagram. If you don't know the V and I, you just move on to the next diagram. But every time you open up a new diagram, make sure you write the equation, whether the I is equal or the voltage is equal, whether the the voltage added up or it's the current that added up. Then from there, you know that the added up equation, you have 2 unknowns usually, or 3 unknowns sometimes, and to find those unknowns using Ohm's law. Then you can verify the answer of your Ohm's law by adding it up, seeing whether it matches with the value at the back over or not. Okay, so this process here is a standard process. I'm not going to explain too much. If you have any question, please refer to the example videos. Next, question 4. A rectangular coil 8 cm times 6 cm has 50 turns. Initially, the plane of the coil, spelling mistake. The plane of the coil is 30 degrees to a magnetic field of 2.8 Tesla. When the plane is flipped so that it's perpendicular to the field in 30 milliseconds, calculate the change in magnetic flux linkage and the induced EMF. So here, I think it's a change of angle equation, because a change of angle question, and it's Faraday's law and Lenz's law, but change of angle because the plane is flipped. The plane is flipped means by you're going to rotate the plane somehow, so you change the orientation of the plane. So maybe I should draw an initial situation and a final situation. Initially, they say that the plane of the coil is 30 degrees to a magnetic field of 2.8 microtesla. So maybe we set the magnetic field to be pointing to the right first. Okay, they didn't mention it, but let's just simply assume that it's pointing to the right. So this is a magnetic field and it's 2.8 Tesla. So your coil here is going to get represented by a line. So if you think of a coil, a rectangular coil, right? Let's say this is a rectangular coil, but you're viewing it from this angle. So what you're seeing is only the plane of the coil. This is the coil. Look at it from the side of it. You're only seeing one line, right? So that line here represents the plane of the coil. So they say that the plane of the coil is 30 degrees to the magnetic field. So let's use green to represent the plane of the coil. So let's say the plane of the coil is over here. Label as the plane of the coil. And this plane of the coil is making an angle of 30 degrees to the magnetic field. Plane of the coil, 30 degrees, magnetic field. Okay, what do we know about this coil? We know that the area is 0.08 multiplied by 0.06. And we know that the number of turns is 50 turns. Okay, so that is the initial situation. But after that, what happens is you're going to rotate the coil, right? So if you rotate the coil, the magnetic field is left untouched, so it still should be the same magnetic field. So I'm going to draw the same magnetic field here. B is equals to 2.8 Tesla. But now they say that the plane is flipped so that it is perpendicular to the field. So the plane is now perpendicular to the field. So if the field is horizontal, then that means the plane of the coil should be vertical, so that it forms 90 degrees. So right now, this is the plane of the coil. So it makes an angle of 90 degree to the field, and this whole process here takes out a time of 30 milliseconds. So that's the duration for this to occur. Okay, so there's many ways you can try to determine this. Okay, but if you look at the question asks for change in magnetic flux linkage. So let's do change of magnetic flux linkage. Change is delta, magnetic flux linkage is capital phi. So you have to calculate phi final, you have to minus it with phi initial. Okay, so we know that magnetic flux linkage, the equation is MBA cos theta. So it will be MBA cos theta final minus MBA cos theta initial. Okay, but we have to be very clear what has changed, what remained constant. The number of turns is still 50 turns even though you rotate the coil. The magnetic field is left untouched, initial and final is still 2.8. The area is still the same coil, so the same coil, the area doesn't change. So you know the MBA here, they are the same MBA for the initial and final, so we don't need to differentiate as initial and final. But we know that the angle initially was a certain angle, but final it was another angle. So this one, the theta, we definitely have to differentiate to be theta final and theta initial. Okay, so if you do this, then right now we can factorize out MBA because those are common things we can factorize out. So you are left with cos theta final minus cos theta initial. Okay, I hope everybody is clear that this theta here is the angle between B and A. Okay, so B is straightforward, but A here is what many students might have trouble. Remember that the direction of A must always be perpendicular to the plane of our coil. Okay, so this is where students make mistakes. The direction of A has to be perpendicular to the plane of the coil. So if this is the plane of the coil, you need to find where's the direction of A, right? The direction of A should be perpendicular to the coil. So perpendicular, this is perpendicular. This is a 90 degree line. But whether the area should be pointing in this second quadrant or in this fourth quadrant, well, we usually try to pick the area, direction of area to be similar, in the similar direction to B. So B is to the right? So we pick the arrow that is pointing towards the right hand side, which is the fourth quadrant. So this here will be our area vector. So this is A, whereas this is B. Okay, so this is B, this is A. So we can see that the angle, initial angle between B and A, the angle is taking this 90 degree minus 30 degree. So you can see that the angle between B and A is actually 60 degree initially. So for the final situation, this is the plane of the coil. We know that the plane of the coil, the direction of A must be perpendicular to it. So the direction of A should be along this line over here. You can pick either it's pointing to the left or pointing to the right, but we'll pick the direction of A to be similar to the direction of B. B is to the right, so we'll pick the right hand side to be our area, direction of area. So this is A. So if this is A, this is B, the angle between A and B, they are in the same direction, so the angle between them should be 0. Okay, so here you can make a conclusion. Theta initial is equals to 60 degree, theta final is equals to 0 degree. Okay, so now we can do our substitution peacefully. So number of turns is 50, the magnetic field is 2.8, the area in between them is 0.0, and the area of the coil is 0.08 times 0.06. Okay, then you have your cos 60 degree minus cos 0 degree. Sorry, wrong. Final minus initial. What am I doing? Final minus initial. Final is 0. So cos 0 minus cos theta initial. Theta initial is 60. Okay, so calculate this. You'll get 42 divided by 125. I think this is Weber, right? Okay, which is equivalent to 0.336 Weber. Okay. Next, they ask for the induced EMF. Induced EMF we know can be determined through Faraday's law. Induced EMF is equal to the negative change of magnetic flux divided by time. But since we want to substitute the change in magnetic flux up there, we need to substitute the duration down here. So it's better that we change the equation to be average induced EMF, so that it can be delta phi over duration. So if we change it like this, only we can substitute above and below. So above we'll be substituting the change of magnetic flux linkage that we obtained from question A. So that is 0.336. Below we're going to substitute the duration for it to happen. For it to change from initial to final, the time taken is 3 milliseconds. 30 milliseconds. Oh, almost make a mistake here. It's not 3 milliseconds, it's 30 milliseconds. Okay. So 30 milliseconds. So the answer I'm getting is negative 11.2 volt. Okay. So let me think about the question whether everything makes sense or not. Data final, then at its time it should be maximum minus 1. Positive change of phi, positive change of phi, negative. Makes sense? Okay, so that's it for this question. Let's move on. Let's try to solve this problem here. We have a 6 Henry inductor. So this is inductance of 6 Henry, which has a resistance of 24 ohm. So this is a resistance, and it's connected to a battery of 12 volt. So they ask you to calculate the energy stored in the inductor when the current is maximum. Okay, so you can think of it like this. You have a battery which is 12 volt. You connect it across an inductor, and they tell you that this inductor has a inductance of 6 Henry. At the same time, it has a resistance of 24 ohm. Okay, so what happens when you connect this battery is the current will change. Okay, initially, because there's no battery, there's no current, right? But once you install this battery, the current will flow in this circuit. But it is not immediately, the current should have a maximum value, which you can calculate using V is equals to IR. Okay, this is how you obtain the current. You know it's 12 volt. You know the current across them should be 0.5 amp. Okay, so this is the current that will be flowing through this circuit over here, and it's 0.5 ampere. But the thing is, this 0.5 ampere doesn't come in immediately. It's not that you connect the power supply immediately it increases to 0.5 ampere. Why is it not immediate? It's because you are connecting it to an inductor. If you remember inductor, right? If you connect it to the battery, you cause an increase in the current, right? So there's an increase in current flowing through the inductor, but because there's an increasing current flowing through this inductor, you create a back EMF in the opposite direction. So if you create an EMF in the opposite direction, right, you slow down the increase of this current to 0.5. Okay, it is increasing from 0 to 0.5, but this process here is slowed down because there's a back EMF trying to oppose this increase of current. So your current will still increase from 0 to 0.5, but it will take a longer time because there's a back EMF here trying to slow down the process. Okay, so that's why they mention when the current is maximum. Yes, the current is indeed maximum at 0.5 ampere, but it will take some time for it to reach 0.5 ampere, and they're interested in when it reaches 0.5 ampere, what is the energy stored in the inductor. We know the energy stored in the inductor is just half Li squared, so I believe you can continue with the substitution. Inductance is 6.0, the current is 0.5 ampere square. Okay, so many students, when they encountered this question last year, I remember they think of it as an AC question, but this is not AC at all. Okay, Why is it not AC? Because they are not connecting it to an AC power supply. They are connecting it to a battery. So battery is a DC voltage. So what you have here is a DC circuit. So it's not chapter 6, it's chapter 5. They are giving you this resistance and inductance here just to let you think of the concept in which the current should be increasing across the duration. It will increase from 0 to 0.5. Then once it reaches maximum, you can find the Imax. Okay, and Imax here allows you to determine Umax, which is the maximum energy stored, which is 0.5 for its current. Okay, so that's it. That's the energy stored in the inductor when the current is maximum at 0.5 ampere. Next, question 5. You have a 30 watt bulb is connected into a 120 volt of an alternating source. So bulb here, we will just assume it to be just pure resistance. So in this case, you have a 120 volt alternating source connecting to a bulb. We can just think of it as a pure R circuit over here. Why is it pure R? Because bulb, how it works, a normal bulb, how it works is by you have a filament inside, you pass through current. Because there's a great resistance, it will cause a lot of heat to be generated, a lot of energy to be generated when the current passes through the resistance of the filament. So that amount of energy generated will be emitted in the form of light. That's why it is a bulb. Okay, so it's a pure R circuit they're talking about here. 120 volt for its alternating source. They didn't mention that it's maximum voltage. They didn't mention that it's peak voltage. They mentioned nothing. When they mention nothing, this is VRMS. Okay, only if they mention specifically its maximum or its peak, then it will be V0. But if they mention nothing, by default it will be RMS value. Okay, so we know that this bulb here is 30 watt. So what are they interested in is the peak current. Okay, maybe we should figure out how to handle this power first. We know that power is equals to, I think they also mentioned this is 30 watt, right? So 30 watt power, I think it should be the average power. The average power is 30 watt. So the average power can be obtained using VRMS multiplied by RMS cos phi. So this is the power average and it's equals to 30 watt. We have the VRMS. The VRMS is 120. We need to find the RMS. But the cos phi should be equals to 1. Okay, cos phi should be equals to 1 because when we talk about a pure R circuit, right? Cos phi is equals to R over Z. But in our case, since there's only resistors in this circuit over here, our impedance will be equals to the resistance immediately. Okay, Z will be equals to R because if you look at a phasor diagram, right? Your phasor diagram only has current, only has pure R, right? So there's only V0 R only. So if you reduce it, you only get R over here. Okay, so there's no XL, there's no XC, so there's nothing to combine. So this R here will immediately equals to Z. Okay, so Z can be replaced with R, so R over R, you get cos phi is equals to 1. So that's why cos phi can be replaced with 1. So from here you can see IRMS is equals to 30 divided by 120, which is equals to 0.25 amp. Okay, so you get your IRMS ready, you can find your I0. That IRMS is equals to I0 divided by square root of 2. So I0 is IRMS is 0.25. I0 is what you need to determine. Square root of 2. So from here you get I0 is equals to square root of 2. You get 0.354 ampere. Okay, for I0. Okay, so that's the peak current. Just make sure the peak current, because it's maximum, right? The value must always be bigger than the RMS value. The maximum should always be bigger than the RMS value, so this makes sense over here. Next, they ask for the resistance of the bulb. Resistance of the bulb. Okay, should be quite straightforward. Okay, we can see that this is a pure R circuit, so the voltage of the power supply will all be dedicated to the resistor, because there's only the resistor in the circuit, right? So everything in the power supply will be dedicated to this resistor only. So we can say Vrms is equal to Vrms R. So we also know that Vrms R, or the voltage, the voltage across the resistance, is equals to IR, right? Okay, so we can say Vrms is equals to Irms times R. Okay, in usual situation, it will be Vrms is equals to Irms Z. But like I said earlier, because there's only resistance in this circuit, so the resistance will be the impedance. So you can replace the Z here with R. So it will be Vrms is equals to Irms R. It's not immediate, it should be equal to the Irms Z first. But for this case, because it's pure R, so Z will be equals to R, so we can replace the Z with R. Okay? So now Vrms, we have the value, Vrms is 120. Irms, we have the value is 0.25. So from here, we can find our resistance, R. So R here, I believe should be 480. Okay, 480 ohm, that's the resistance of the bulb. Next. Question B, you have an AC voltage with a voltage of 10 sine 4 pi t, where V is in volt, T is in second, connected to a resistor. They are very kind here, they always ask pure R circuit, I wonder why. Okay, so this one is a accumulator. You're connecting it to a pure R, there's only a resistor. Okay, then the information they give you here is V is equals to 10 sine 4 pi t. Always remember, when you get an equation like this, compare it with the general equation. So this is the equation for this particular circuit. You compare it to the general equation, V is equals to V0 sine omega t. We can make a comparison and say that V0 is equals to 10 volt. At the same time, we can see that omega is equals to 4 pi radian per second. Okay, so this omega here, you know that can be related to the period, can be related to the frequency using this equation. Omega is equal to 2 pi over period. Omega t is equals to 1 over f. Period is equals to 1 over frequency. Omega is equals to 2 pi f. So now you know this already. If they ask for determine the period t, it should be quite straightforward. You know that omega is equals to 2 pi over period. So omega is 4 pi. So it should be equals to 0.5. Okay, next they ask you to sketch the VT graph for one complete cycle. One complete cycle. So voltage against time. Your voltage is in volt. Your time is in second. They want one cycle, and this is a sine graph, right? So you draw one cycle only. Okay, not very good. It should have almost equal height. Okay, so label everything that is possible. You know that the maximum is 10, that's V0. So this is positive 10, this is negative 10. You know that for one cycle, the period is 0.5, so you can label this to be 0.5. Okay, so this will be a VT graph for one complete cycle. Okay, next. Question C. Okay, so here comes the combination circuit. Okay, let's solve this question here. Figure 5 shows a 1.6 times 10 upon negative 3 ampere current. So there's this much current flowing through the 20 kilo ohm resistor and the 0.45 microfarad capacitor, okay, which are connected in series to a 50 Hz AC supply. This current here will be the current across the whole circuit, because there's only one loop only, there's no junction. So everywhere the current should be the same, okay, because there's no other branches to flow away, there's no other branches to merge the current. So this current will be the current everywhere in this AC circuit, okay. But this is RMS current, because they didn't mention its peak, they didn't mention maximum, they didn't mention peak. So immediately we can assume that this is IRMS. So we should label IRMS is equals to 1.6 times 10 to the power of negative 3 ampere. Flows through a 20 kilo ohm resistor. So this is 20 kilo ohm resistor. This is 0.45 microfarad capacitor connected in series with a 50 Hz AC supply. So power supply, the frequency, I usually label it at the power supply as well. Okay, so maybe I'll start this situation by drawing a phasor diagram first. I usually like to draw phasor diagram because it helps us illustrate how to find everything. So here we always usually set our current to be to the right. And because this is an RC circuit, you have the voltage across your R, which is in the same direction as the current. So this is V0R. And you have your voltage across the capacitor, which is lagging by 90 degrees. So it should be somewhere down here. So this should be V0C. So V0R is equals to I0 multiplied by R. V0C is equals to I0 multiplied by XC. And the combination of these two voltage will be the voltage across the overall circuit. So this voltage across the overall circuit is just V0 without any subscript because it's not across the resistor, it's not across the capacitor. This will be equals to I0 Z. And this angle over here should be called phi. Okay, so you know this is the phasor diagram. You can draw a reduced version of it as well, which is you take every voltage over here, you divide by the I0. So if you divide by I0, you have your resistance pointing in this direction. If you divide by I0, you have XC, your capacitive reactance pointing in this direction. If you divide by I0, you see that the combination of the R and XC will be what you have over here, which is the Z, and this is phi. Okay, so if you want to find a capacitive reactance is XC, right? You need to have Z, you need to have R maybe. So how do you find your Z? You have your current, which is RMS. Okay, you know that you can draw the RMS version of things. So VRMS is equals to IRMS multiplied by Z. VRMS R equals to IRMS multiplied by R. If VRMS C is equals to IRMS multiplied by XC. I think you have the capacitance. If you have the capacitance to find XC, I think it should be straightforward. Okay, XC is just 1 over omega C, or you can open it up to become 1 over 2 pi FC. Okay, this one is just the definition of capacitive reactance. So frequency here we know is 50 Hz. Capacitance here is 0.45 micro. So if you calculate it, you get 7073.6 ohm as the capacitive reactance. Again, reactance is the ratio between V and I. So V and I, the ratio will be in the unit of ohm, just like what we have for Ohm's law. Okay. Okay, that's right. Okay, then they ask for the VRMS, RMS voltage of the AC power supply. So they're asking for power supply, means by they're asking for the overall V. So the overall V in RMS, so they're asking for VRMS. So if they're asking for VRMS, we know that VRMS is equals to IRMS multiplied by Z. You have the IRMS is 1.6 times 10 to the power negative 3. You just need to determine your Z. How do you determine your Z? You can determine it from Pythagoras theorem, because you can see that Z is the combination of R and XC in x-axis and y-axis. So you can see that it's actually Pythagoras theorem, R squared plus XC squared. So the R over here should be 20k, 20 times 10 to the power of 3 square. XC over here, XC already determined earlier, it will be 7073.6 square. Okay, so answer square plus 20k square, so square root of it will be 2.12 times 10 to the power of 4 ohm. Okay, so this is what we are going to put in here, 2.12 times 10 to the power of 4 ohm multiplied by 1.6 times 10 to the power negative 3 for IRMS. you get your VRMS to be 33.94. Okay, so this is the RMS voltage of the power supply. Okay, let me double check everything. Okay, should be fine. Next. Question 6. A student who is standing 1.52 meter in front of a spherical mirror produce a rear inverted image 18 cm from the mirror. So it asks you to determine his new position from the mirror to get an upright image that is twice the size. So there's an initial situation, there's a final situation, because they ask for new position from the mirror. So let's try to talk about the initial situation. Initial situation, they say student standing 1.52 meter in front of the mirror. Okay, so from here this tells us the distance. Okay, let's draw a rough idea of the diagram. So your mirror will be somewhere here. So your student is the object. I believe he's standing in front of the mirror. So this is your object, or the student. The student is standing 1.52 meter in front of the mirror. Produce an inverted image 18 cm from the mirror. Okay, so we know for this one, this is U is equal to positive 1.52. Why do we know it's positive 1.52? It's because for an object to be placed here, the light will be coming out from the object. Okay, you come from the object, you hit towards the mirror. So this is where the incident ray is. So we know the incident is over here. And because what you have here is a mirror, your light will get reflected back towards to the left. So the reflected ray should be over here. Okay, incident is on the left hand side, reflected also on the left hand side, because your light will bounce back. Okay, so if your object is on the same side as the incident, object same side as incident, that's why your object distance U here will be positive. Okay, next it says that it produces an inverted image. Okay, inverted image, first thing you can think of is, if it's inverted, you know that the M and your HI is negative. Okay, this is what you know from what you learned in class. At the same time, you know that inverted image means by it's real, because real pair with inverted, upright pair with virtual. So if it's a real image, you know that your V later is positive. Okay, so if V is positive, it means by your image is on the same side, image is on the same side as the reflected ray. So if image is on the same side as the reflected ray is on the left, right? That means 18 cm here will be from the mirror to the left, because you want to be at the same side as the reflected ray. Because V is positive, it's a real image. So that means by the image should be inverted and it's real, and the distance of it from the mirror will be 18 cm to the left, 0.18. 18 cm from the mirror. Okay, initially if you read 18 cm from the mirror, you know that this is the distance of the image from the mirror, right? So you can write V modulus is equals to 0.18. Why do you write modulus? It's because just that it's because we don't know the sign of V, but after we read that, oh, actually I already determined the sign of V to be positive, I can immediately open up the V to be V is equals to positive 0.18. I write modulus V when I'm not sure whether it's positive or negative, but once I already check that it's positive, then I can transform it by breaking away the modulus and write it as a positive value, but 0.18. Okay, so they ask you to determine the position of from the mirror to get an upright image that is twice its actual size. So that's the final situation. Final situation, they want you to find U, find the new U, so U prime. Okay, so they want to get an upright image. So if they are asking for an upright image, immediately you should think that your M and your HI, both of them is positive. Okay, that's just what you learn in concepts. Okay, then because it's upright, it must be paired with virtual, right? Virtual paired with upright, real paired with inverted. So if it's a virtual image, you know that V is negative, and you know that image should be on the opposite side of the refracted ray. Reflected ray, sorry. Reflected ray. Okay? So then they say twice its actual size. Okay, if you read carefully, to get an upright image that is twice his actual size. So if the student, has a certain height, twice its actual size means that the image is larger. So the image is larger, is magnified. So we can say that the magnification modulus M is equals to 2. Okay, because you have already twice the size of the object. But I put modulus M is because I don't know the sign of the magnification yet. But if I look upwards, I see that for final situation, M, because it's upright, M is positive, right? So I can break open my modulus and say that M is actually equals to positive 2. Every time I check my sign, if I know my sign, I write down the sign. Even though it's positive or negative, no matter whether it's positive or negative, I write down the sign. Even if it's positive, you can remove the sign, right? But I still write as positive 2, just to reaffirm myself that I have already checked the sign for magnification, and the sign for magnification is indeed a positive value. So M is equals to positive 2. Okay, so every time I check a sign, you will see that I write in the sign. Even though it's a positive value, I will still write in the sign. Okay, so now what do we do with the information we are given with for the initial situation? They give us the U, they give us the V. I believe the intention is to find the F, which is the focal length of the mirror. And once we have the focal length of the mirror, because we are not changing the mirror, the focal length can be brought over to the final situation. Okay, so let's do it for the initial situation first. Initial situation, you have 1 over U plus 1 over V is equals to 1 over F. To find the focal length, your U is positive 1.52. Put in a positive sign just to make sure that you already checked the sign of U and you already checked the sign of V, and both of them should be positive. And from here, you get your focal length. So your focal length over here should be equals to positive 0.161 meter. Okay, so if you look over here, they already know that this is a real image, right? Okay, if you know that it's a real image, we can actually make further deduction. Okay, real image means by it's not virtual, it's not upright, it's not diminished anymore, right? If it's not virtual, upright, not diminished, we know that it is not made by a convex mirror, it is done by a concave mirror. Okay, convex mirror can only produce image of one type of characteristics, which is virtual, upright, and diminished. So if your image is not virtual, upright, diminished, immediately it is not made by a convex mirror, it is made by a concave mirror. So concave mirror, we can draw in the concave mirror. So concave mirror looks something like this. So if this is a concave mirror, we can think that if we extend the circle, you can see that the center of curvature is somewhere on the left, right? So center of curvature is somewhere on the left. So on the left means by the center of curvature will be on the same side as the reflected ray. COC and the reflected ray are both on the left hand side of the mirror. So that means by our R is positive. So if our R is positive, then that means by our F is positive. Which is true for our case over here, we do indeed get a focal length that is positive. Okay, so maybe if you want to add on some more information, you can say that this is a concave mirror. Okay, next, you are going to use this focal length to solve the second part of the question, which is the final situation. So you're asked to find the new object distance. You need to find the new v. It's the same old f. Okay, so we know that m here is equals to positive 2. So if m is equals to positive 2, m we can open up to become negative v over u, right? So from here you can see that v is equals to negative 2u. So this is what we are going to substitute. It's a new v, new u, new v, new u. So 1 over u prime plus 1 over negative 2u prime is equals to 1 over positive 0.161. So there's only one unknown. You can key into your calculator to determine what is it. It will take some time because I'm using the soft function. I'm too lazy to manipulate the algebra. Okay, so what I get here is positive 0.0805 meter. Okay, so let me double check if it's right or not. Okay, should be fine. So that's u prime, the new position from the mirror. Next, a biconvex lens has surface with radial curvature 18 cm and 20 cm. So this is a biconvex lens, but it is an asymmetrical kind of biconvex lens. One side should have 18 cm for its radius of curvature. One side should have 20 cm for its radius of curvature. Okay, so when an object is placed 24 cm in front of the lens, a rear image is formed 32 cm from the lens. Okay, determine the... Okay, so maybe you can extract a few information. It says that it is biconvex. Okay, biconvex lens, first thing you know that it is a converging lens. If you know it's a converging lens, you will know that the focal length will be a positive focal length. Okay, then after that they say that it's biconvex, right? So if it's biconvex, this will be surface 1, this will be surface 2. For surface 1, the center of curvature is on the right hand side. For surface 2, your center of curvature will be on the left hand side. We know that we usually place our object somewhere around here, right? So this will be our incident. Then because it's a lens, the light will get refracted to the other side. Okay, so we can see that for radius of curvature of 1 should be positive because the COC is at the same side as the refracted. Center of curvature is at the same side as the refracted ray. Same side means positive. So R1 here is positive. But COC for a second surface, the center of curvature is on the left hand side, which is the opposite side of the refracted ray. So from here, opposite side, we know that R2 here will be negative. Okay, so that is what we can know from the word biconvex lens. So now they say that has a radii of curvature of 18 cm on and 20 cm, R of 18 cm and 20 cm. Okay, so from here we can really say that it's okay to put R1 or R2, one of it to be positive 0.18 meter. You can put R2 to become negative 0.20 meter. I think this is the same as even if you choose to flip it. If you choose to flip it, I think you will still be correct. If you want to put it as 0.20 meter, you want to put R2 to be equal to negative 0.18, I believe you will still get the same answer. Because the lens, if you flip it this way, then you're changing who is 18, who is 20 cm. You still get the same answer because the lens, when it's flipped, the focal length should still be the same. Okay, so now they say object is placed 24 cm in front of lens. So this is telling us that the object has a distance of 24 cm from the midplane of the lens, 0.24 meter. So this is U is equals to positive 0.24 meter. Why is it U is equals to positive 0.24? It's because object is at the same side as the incident ray, so same side U should be positive. A real image is formed 32 cm from the lens. So if they say it's real image carry two meaning. One, V is positive, or in other words, your image is at the same side as the refracted ray. Okay, so if your image is at the same side as the refracted ray is on the right, so your image should be on the right hand side, because same side as the refracted ray right hand side, image right hand side. So image is real must pair with inverted. So that means by this distance here should be 0.32 meter. Okay, so that's the first thing you can know. Second thing that you can know is real pair with inverted. So if it's inverted image, then the image M and your HI both should be negative, R negative. Okay, so it's virtual, it's inverted, and because they say it's 32 cm from the lens, this is telling you the image distance, right? So it's telling you that V modulus is equals to 0.32 meter, but once you already determine that V is positive, right, you can open up the modulus V to become V is equals to positive 0.32 meter. Okay, so first thing they ask you to determine is the focal length. You have your U, you have your V. I think finding focal length should be quite straightforward. Next, they ask for the refractive index, which you need to relate to the lens maker equation. Okay, so let's start with question number 1 first. Question 1, you have 1 over U, 1 over V is equals to 1 over F. 1 over U is positive 0.24. 1 over V is positive 0.32. Very convenient to give everything positive. So your focal length will be equals to 24 over 175, which is equivalent to 0 positive 0.137 meter. Okay, we see that our focal length is a positive value, which match with our prediction because it is a converging lens, so f must be positive. So it further reaffirms that our answer most probably is fine. Okay, next they ask for refractive index. Refractive index, you have to refer back to the lens maker equation where 1 over f is equals to n material divided by n medium minus 1 over R1 minus 1 over R2. So just substitute 1 over f should be 175 divided by 24. You're just flipping the focal length. N material is what you need to find. I believe the medium is just air. You are putting the lens in a normal situation, so the surrounding is air, so it's 1.00 minus 1 over R1. If you put positive 0.18 minus 1 over R2, we put negative 0.20. Okay. So you get M material to be equals to 1.69 for its value. Okay, so let me double check. Okay, seems fine. So this is the refractive index of the lens material, 1.69. Most probably is glass, I think. Okay, next question. A thin film of soap floating in air has a refractive index of 1.33. So this is a thin film question. Calculate the minimum thickness of the film that will reflect yellow light of wavelength 590 nanometer. When you are encountering a thin film question, always make sure you draw these two lines so that you have medium 1, medium 2, and medium 3. Your thin film is made of soap, right? And this soap is suspended in air. Okay, it's floating in air, so above the soap must be air, below the soap will also be air. So always make sure for a thin film question, determine what are your 3 medium first. So once you have your 3 medium, you can put in the index of refraction. For air, it should be 1. For the thin film, the soap will be 1.33. Why do you want to draw this diagram over here? It's because you want to check whether there's any phase change happening at both the boundary or not. Okay, if you go from small index of refraction to big index of refraction, there will be phase change. There will be phase change. Or if you go from big index of refraction to small index of refraction, there will be no phase change. So in this case, you're going from 1.00 to 1.33 for this boundary over here. You go from small to big. So we can make a conclusion here, there will be phase change. Next, for this boundary over here, you're going from 1.33 to 1.00. From here to here, big to small, no phase change. Okay, so from here, we can conclude that there's only one phase change that happens. Okay, continue to read the question. They ask for minimum thickness of the film that will reflect yellow light. If you want to reflect the yellow light, that means you want it to be seen clearly. If you want it to be seen clearly, you don't want to cancel out the light, right? If you cancel out light, you cannot see it anymore. So you want to see it clearly, that means you want it to be constructive. Okay, if you want to reflect, that means you want to see it. If you want to see it, it means it has to constructively interfere. Okay, you can refer to the concept video for more idea. So right now you can see that this is a question involving one phase change and it involves a constructive interference. Okay, so for one phase change, constructive interference, our equation will be 2nt is equals to m plus half lambda. How do we get this equation? I actually did a table. If it's 0 phase change, your constructive equation will be 2nt is equals to m lambda. If it's destructive interference, your equation will be 2nt is equals to m plus half lambda. But this is if you have no phase change at all. If you have one phase change, what you need to do is you need to cross the equation. And if you have two phase change, you need to cross the equation once again. Okay, so for here, you are doing one phase change constructive, right? One phase change constructive, so it comes from this equation being crossed to the left hand side. So this is the equation. Okay, we can do our substitution actually. This will be the thin film refractive index. We want a minimum thickness, right? So if you want minimum thickness, that means I want to keep the left hand side to be a minimum value. So the right hand side should also be minimum value. But we know that the lambda is fixed already. The lambda is a yellow light, so it's 550 nanometers. So that is fixed. So if you want to keep the right hand side to a minimum, that means my m here will be a minimum m. So what's the minimum m? The minimum m will be 0. Okay, if you sub in 0, you will still get a value for t minimum. So that's the minimum thickness. If you sub in 0 and your thickness becomes 0, then that's illogical, because that means there's no thin film anymore. As long as there's a thickness, then it's fine. So the smallest thickness that you can have is if you substitute 0 for m minimum over here. So you're going to substitute with 0. So if you substitute with 0, you get an answer of T minimum is equals to 1.109 times 10 to the power of -7 meter. Okay, so that means if this soap here has a thickness of 1.109 times 10 to the power -7 meter, then the light that arrives at this soap, right, okay, it will undergo reflection and refraction. This one you can refer to the concept video. But you see that these two yellow light here will constructively interfere. So you are able to see their reflection very clearly from top. Okay, so that's the idea. This is the minimum thickness. Of course, you can find other thickness which can have constructive interference as well by changing it from 0 to 1 to 2 to 3 and so on and so on. Then you see different thickness that can allow you to reflect yellow light constructively. Okay, next. A 632 nanometer wavelength light passes through a double slit at normal incidence. So you are shining light of 632 nanometer through a double slit. The interference pattern is formed on the screen at 1.40 meter away. So this screen is 1.4 meter away from the double slit. And as the distance between the second order bright fringe is 0.23 millimeter. Distance between second order bright fringe. Okay, so means by the second order bright fringe has a distance of 23.0 millimeter. So there's two second order bright fringe, right? One is at the upper half of the screen, one is at the lower half of the screen. So the two second order bright fringe, the distance between them is 23.0 millimeter. Okay, then ask us to calculate the slit separation, which is the distance between the two slits. This question is actually quite fresh. Maybe you need a little bit more explanation. So this is our double slit, and we have our screen somewhere over here. So this is slit, this is screen, and they tell us that the distance between the slit and the screen is 1.40 meter away, and we are shining light of 632 nanometer. So this will be light that are at normal incidence, means by they are arriving at 90 degree, but the wavelength over here is 632 nanometer. Okay, so these lines here are representing the wavefront of the red light. I think it's maybe red light or orange light, somewhere around there. Okay, so the kind of pattern that you should see for double slit should be something like this. think you need to draw it for both sides because you want the distance between the two 2 second order bright fringe, right? Oh, butchered the drawing. Never mind, as long as you understand what's happening. Okay, so everything here that you see here are called bright fringe. Everything that you see here are called dark fringe. What am I drawing here is the graph. Okay, you can think of this as brightness against position. Okay, so this is what you usually draw. Basically, it's bright, dark, bright, dark, bright, dark. So you can think of it to be something like this: bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. Okay. So this is what the kind of thing that you should be imagining based on this graph over here. Okay, so they say that the distance between second order bright fringe is 23 millimeter. So if you see the word order, immediately you should be alert. The value in front over here will be the order number. If it's an order number, that means by our m is equals to 2. Okay, so we know that for double slit, m starts with 0. For double slit, m starts from 0. Why is it so? You can refer to the explanation video. M starts with 0. But if it's single slit, then your m starts with 1. Okay, but this is double slit situation, start with 0, so the center one is 0. So here it will be 1, here will be 2, here will be 1, -1, here will be -2. And they say that the distance between the second order bright, so this is second order, m is equals to 2. This is second order, m is equals to 2. And the distance between them right now is 23.0 times 10 to the power -3. This is the distance between the two second order bright. Okay, so how do you get this value? Actually, any kind of y that you want to determine has to start from the center, right? So if you start from the center, you can see that this measurement here is actually finding this is y2 bright. Okay, because you need to substitute m is equals to 2 and it's a bright fringe, so this is y2 bright. And you can see that down here, this is also y2 bright. Okay, so you can see that from this diagram over here, 2 times of y2 bright is equal to this value over here. So we can make a conclusion: 2 times of y2 bright is equals to 23.0 times 10 to the power of -3. So y2 bright, we can expand it. This is m lambda d over d, so this is 2 lambda d over d is equals to 23 millimeter. So this will be 4 multiplied by lambda. Lambda is 632 times 10 to the power of -9. Distance between slit and screen is 1.40. Distance between the two slit, distance 1.40 here is the distance between slit and screen. D here is the slit separation. Small d here is slit separation, which you are asked to find. Is equals to 23.0 times 10 to the power of -3. Okay, so we can calculate it. So you find that the slit separation D is equals to 1.54 times 10 to the power of -4 meter. Okay. should be fine. So this is the slit separation. Next, question E. For demonstration, a student uses a razor blade to create a slit of width 9.35 times 10 to the power negative 5 on the aluminium foil. So they create a slit, right? So this is a single slit question because there is only one hole or one line only. When he shines a laser pointer with wavelength of 680 nanometer on the slit, a diffraction pattern is observed on the screen. The width of the central bright is 8 cm. Calculate the distance of the screen from the slit. Maybe I'll sketch a situation to illustrate how everything pieced together. So this is a single slit, so I'm going to put one single slit on the slit side. So this is the slit. This is the screen. So they create a slit of width A is equals to 9.35 times 10 to the power of negative 5 meter. So this is the width of the slit, the size of the slit. Then they shine a light of 680 nanometer. So this is probably red, I think. Okay, so this is the light that is shining onto the slit, and it has a wavelength of 680 nanometer. So you form a diffraction pattern on the screen, and I believe you are quite clear with how the diffraction patterns looks like. Okay, for diffraction pattern, you need to know that the central bright is twice the thickness of the other bright. Okay, so you can see that I draw my central to be twice the thickness. Central here is twice the thickness of the fringes on the side. So this is a diffraction pattern. And they say that the width of the central bright is 8 cm. So this is the central bright, and the width should be within these two lines over here. So this one, they say that the width is central bright is 8 cm. So this is 0.08 meter. And we know that this central bright here can actually be obtained. Okay, again, single slit. M starts with 1, right? But you cannot label the central. Okay, if you want to know the why is it so, you have to refer to the concept video. But basically, if this is your pattern, you cannot label the central bright. Other than that, you can label. So this will be you cannot label here, but here you can label. So the first thing that you start with 1, right? So that means by here should be 1, then here should be 2. So here should be 1, here should be 2. Okay, then of course for the bright you can start with this bright but not the central bright, so this should be 1, this should be 1. Okay, we can see that if we want to measure this 0.08 here, it can be measured by first measuring from the center. It's always from the center. For Y, it's always starting from the center. So this one over here is Y1, but this is dark because we are seeing that the limit here is where you see dark. Okay, over here is also Y1, and it's also dark. Okay, why is it 1? Is because here I label M to be equals to 1. At the same time, this is a dark fringe, so I'm going to write it as dark. Okay, so you can see that width central is equals to 2 times of Y1 dark. Okay, if you refer to the equation sheet for dark for single slit, the equation is 1 lambda D over A. This is for dark equation. W central. Okay, so the width of central is 0.08. It's equals to 2 times lambda 680 nanometer. The distance between slit and screen, did I mention it? No, that's what you want to find. And the width of the slit is 9.35 times 10 to the power of negative 5. So from here you can find the distance between the slit and the screen. So the distance here is 5.5 meter. Okay, so So that's big D. Okay, next question 7. Okay, a photon is a type of elementary particle and always move at the speed of light in vacuum. So light, this is a light particle, light behaving as a particle known as photon. Okay, given that the de Broglie wavelength of this particle is 800 nanometer, calculate. Okay, timer times is up. Okay, last two questions, we'll just finish it very fast. So they asked us to calculate the de Broglie, they say the de Broglie wavelength of this particle. Actually, the statement is a bit misleading, I think. Photon is a light. So for light, right, we are not going to call it de Broglie wavelength, because de Broglie wavelength, right, another name of it is matter wavelength. So only if something is a matter, only it will have a de Broglie wavelength. Light is not a matter, so it is not supposed to have a de Broglie wavelength. Okay, so we will just call it as given that the wavelength of this particle is 800 nanometer. Then now it makes more sense. Okay, so light, the momentum. Okay, for this particular chapter, there's a few mind maps that you need to know. There's a mind map for matter. There's a mind map for light. Not mind map, but more like equation map. For light, you need to know how to relate between the energy, the wavelength, and the momentum. For energy and wavelength, it can be related through E is equal to hc over lambda. For wavelength and momentum, is related by P is equal to h over lambda. Okay, for matter, you need to relate a few more things. You need to relate between accelerating voltage V or accelerating potential V, relate to the kinetic energy of the particle K, relate to the momentum P. You have to relate either to the speed V or relate to the wavelength lambda. So this one, you need to know that K is equals to EV, K is equals to P squared over 2M, P is equals to MV, P is equals to H over lambda. So this is the kind of mind map that I usually keep in my mind when I solve the question of this particular chapter. So light, a photon is a light, so we are going to refer to this mind map. They ask for the momentum, so momentum is P is equals to H over lambda. So rather straightforward, P is equals to H over lambda. H is a Planck constant, you can refer to it in your constant sheet, 6.63 times 10 to the power negative 34. The wavelength given to us is 800 nanometers, so 800 times 10 to the power negative 9. So from here we can get our momentum to be 0.29 times 10 to the power of negative 28. The unit for momentum is kg ms negative 1. You can derive it from here, kg ms negative 1. Okay, seems fine. Then next, they ask us to calculate the mass of the photon if it behaves like a particle. So now we are going to assume that this photon here behave like a photon. It is a particle already, but here I think they are saying that you behave like a matter. Maybe if you behave like a matter, then you need to consider this equation map already. So mass of a photon. So photon technically is massless. In real life, photon is massless because photon is light. Light has no physical mass. Okay, so light is massless, but now they ask you to assume if photon is a matter. If your photon is a matter, then matter is physical, right? So you have a mass. So they ask you to determine the mass of the photon. Okay, you are given a wavelength and you want mass. You know that mass is either here or either here. Okay, but you have the wavelength and you want mass, and you know that the particle is traveling at the speed of light, so you have the speed. So if you have speed, you have wavelength, you want to find mass, probably you are connecting this way. Speed 3 times 10 to the power 8, that is speed of light in vacuum. Then wavelength, you have 800 nanometers, so you connect it like this, you have m in your equation to find. Okay, so you can say that P is equals to mv, at the same time you can say that P is equals to h over lambda, so you can connect these two equations together and say that mv is equals to h over lambda. So you want to find m, right? So m will be equals to h over lambda multiplied by v. Am I right? Seems about right. Okay, so this is 6.63 times 10 to the power of negative 34. Lambda here is 800 nanometer. It is traveling at the speed of light, so 3 times 10 to the power of 8. This is a theoretically impossible kind of situation, but they are just asking you to assume if it really do happen. So you find that the mass is 2.76 times 10 to the power of negative 36 kg, which is an extremely small value, like near a 10 of a millionth times smaller than the mass of electron, I think. A very, very small value. Okay, seems about right. Okay, so that's the mass of the photon if it behaves like a matter, but it does not behave like a matter, so this is just a theoretical situation. Next, the mass of a helium nucleus is 4.001510 U. So they are giving us the mass of nucleus. This is not mass of an atom, this is mass of nucleus. So we have to use the usual equation that we have for mass defect, which is the mass of proton, total mass of proton, plus the total mass of neutron, minus the mass of nucleus. Okay, there's another version for mass of atom, but in this case, it's mass of nucleus being given in the atomic mass unit. So they ask us to calculate the binding energy of the nucleus in MeV. So we can start by finding the mass defect first. So mass defect, you can, if you remember, is the total mass of proton plus the total mass of neutron minus the mass of the nucleus. Okay, so this is a 4,2 helium. So you can see that A is equals to 4, Z is equals to 2, so number of neutrons should be equals to 4 minus 2 is equals to 2. So here it will be 2 times the mass of proton, I can't remember, I forget to write it here. 2 times the mass of neutron, this is 1 point something, minus the mass of nucleus, 4.001510. Where can I find the mass right now? I think this is 1.8. Let me find the value somewhere here. I think it's here. Physics attack. Wait, I don't have a value here. Chapter 9 worksheet. I want the mass in atomic mass unit. You can refer to the constant sheet, just I didn't copy the value, so I can't remember the value. No, not this one. Proton, neutrons, electron. Yes, this one. Okay. Pspm. Okay, let's continue. Sub in the value. 1.007277, 1.008665. Okay, so if you calculate it, you get a mass defect of 0.030374 U, which you can use to find the binding energy. Binding energy is just mass defect multiplied by c squared. But how we do this? How we're going to do this is we are going to change the mass defect from a unit of atomic mass unit. We change it to be MeV over c squared. So you know that one atomic mass unit is equal to 931.5 MeV over c squared. So this is the mass defect multiplied by c squared. So if you can see that c squared can cancel out, u can cancel out. So you are left with your answer in MeV. So your answer will be 28.29 MeV. Okay, one thing to be careful of when you solve this question is when you're calculating mass defect, please make sure that the number of decimal place here, you do not round it up. So if here there's 6 decimal place, you keep it as 6 decimal place for the mass defect as well. Okay, so if you do that, and if your mass defect is in atomic mass unit, do a conversion to MeV over C squared, then you're able to get your mass defect in MeV. And if they want it to be in joule, you can convert it to EV first, then convert it to joule. But it depends, you just stay flexible, convert it to the unit that they want. Okay, next question. The half-life of a radioisotope as sample is 3 days. So this is half-life. If the initial activity of the sample is this much, so this one is A0. Determine the activity of the sample after 4 days. So this is at some time later A. So you know that the equation here will be A is equals to A0 e to the negative lambda t. Okay, so this one relates between initial activity and the activity after some time. The initial number of radioactive nuclei, this one is N0. Okay, you can refer to the equation map for this chapter as well. A is equals to lambda n. So on the left hand side, you have A is equals to A0 e to the negative lambda t, showing how does activity change with time. On the right hand side, you can see how n change with time, n is equals to n0 e negative lambda t. Then we can see that the number over here, actually we can relate it to the mass. So number of radioactive nuclei is the mass of sample divided by the molar mass multiplied by the Avogadro number. So this is how we usually relate all the equations here. So for the first question, they ask for activity after 4 days. You can use this equation because this relates how the activity changes with time. But the problem here is you don't have lambda. But you know that this lambda here, okay, I forgot to complete it. Lambda here is related to half-life. So half-life is equal to ln 2 divided by lambda. So you can find the lambda through half-life. Okay, so for this equation, you have to make sure that the time unit is consistent over here. Okay, so if you are substituting the half-life to be 3 days, then you have to make sure that your lambda here is also in the unit of per day. Okay, so lambda here will be ln 2 divided by 3 per day. Okay, the unit has to be correct. Okay, next you can continue to use this lambda here, substitute here. When you use this equation, again there's things to be careful about. You have to make sure that A and A0, they are the same unit. Okay, it can be in Curie, it can be in Becquerel, whatever unit prefer. But if it's Curie over here, it should be Curie over here. If it's Becquerel over here, it should be Becquerel over here. Next thing is your lambda and your T. Your time unit has to be consistent. You have to have consistent time unit. So if today I'm substituting ln 2 over 3 over here, then it's in per day, right? Then my time will have to be in days as well. So they ask for 4 days, right? So this is ideal. I'm substituting my time in the unit of days. I'm substituting my lambda in the unit of per day. So they are consistent in terms of unit. Okay, so our activity is in Becquerel. So later we should expect the same unit for the activity after 4 days, which is also in Becquerel. Negative ln 2 over 3. This is lambda. The time is 4 days. This is per day, this is day, so time unit is consistent. This is in Becquerel, so later our answer should be in Becquerel as well. So you get 2.58 times 10 to the power of 3 Becquerel. Okay, so this is your activity after 4 days. Then next question, they ask for initial number of radioactive nuclei, which is when time is equal to 0. You know the activity, initial activity is this much, so you can actually change the equation to be A0. Then what you will get here will be N0. So A0 will be equals to lambda N0. Lambda here, the value won't change with time. Throughout the decay, your half-life is still 3 days. Your lambda is still ln 2 over 3. It never changed throughout the decay process. What changed throughout the decay process is the activity and the number of radioactive nuclei. So initially, if they ask for initial, so you put in the initial value, which is 6.50 times 10 to the power of 3 for initial activity. Lambda here is what you need to be careful about. N0 here has no unit, so you have to make sure A0 and lambda here has the same unit. Okay, right now I'm using a unit of becquerel. Becquerel is the same meaning as per second, so my lambda here will have to be in per second. So I have to convert my lambda here to be in per second. So ln 2/3 per day. Per day means that it's 1 day at the bottom. So I need to eliminate day. I need to introduce second. So 1 day there's 24 hours. 24 hours there's 60 minutes for each hour. There's 60 seconds for each hour. So 2 divided by 3. 2 divided by 3 divided by 24 divided by 60 divided by 60. I'll be getting my lambda to be 2.674 times 10 to the power of -6, and this is per second. Okay, double checking everything. Okay, so this should be what I substitute here for lambda, because I need to keep it consistent between the unit of activity and lambda. Both should be in per second. So this is 2.674 times 10 to the power of -6. So I can calculate my initial number of radioactive nuclei. So I can obtain my initial number of radioactive nuclei to be 2.43 times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the power of 9 nuclei. Okay, so yeah, I think this equation map helps because it helps you see how this is a central equation. Lambda can be related to half-life, A can be related to how activity change with time, N over here can be related to how does the number of radioactive nuclei changes with time. Sometimes you don't have the number of radioactive nuclei, you can determine from the mass of sample by dividing it with the molar mass to obtain the number of mole, multiply by the Avogadro number to get the number of radioactive nuclei. So this is a powerful equation map, and it allows us to see how everything connects together. Make sure when you're solving questions related to this chapter, make sure to check the unit to be very clear in terms of unit. A and A0 same unit. Here the time unit needs to be consistent. Here because N0 is dimensionless, your A0 and your lambda should have the same unit. Becquerel is equivalent to per second. That's why you need to substitute lambda in per second in order to get your N0. Okay, so that's it for this question, and I believe that's the last question for this pre-PSPM, and not pre-PSPM, this is PSPM for session 2022-2023. That's it. Thank you very much. Oops, it seems like I made a few mistakes this time. I made a little bit too many mistakes. Okay, the first mistake that I made was in question 1, actually the first question. They asked for the magnitude and direction of the electrostatic force, right? So I calculated my F21, then I've calculated the angle over here, then I immediately say that this is the angle below positive x-axis. But this is actually a really bad mistake, because the angle that we are talking about is with respect to the x-axis, right? So our x-axis is over here, so the angle that we should be talking about is this particular angle over here. It is this angle that we need to talk about. So even though we managed to get our data, we shouldn't find our data this way. Okay, we should probably label this as data. Okay, if I am able to do correction for this question, I will not label my data over here, I will label my data over here. So if I label my data to be over here, then opposite will be 0.1 instead. So this will be 0.1 to be opposite, then this will be the adjacent instead. So this 0.07 will be the adjacent. So if I have the chance to redo this question, I will do it as tangent data is equals to opposite will be 0.1, adjacent will be 0.070. So from here, I'll be able to get my angle to be 55 degree. So this 55 degree over here will be the angle that I label in this place over here, which is with respect to the x-axis. So this is the correct angle. So the angle that I previously said over here is wrong. So instead it should be 55.0 degree. Okay, so if you change it to 55.0 degree, then this angle should be right, then it's below the positive x-axis, then everything here should be okay. But the mistake of me making over here is I'm doing it with respect to the y-axis, where it should be with respect to the x-axis. Okay, the next mistake that I make is in which question? This question over here. In question 2, I have already calculated the effective capacitance or the equivalent capacitance that I substitute inside this equation to find time constant, right? Everything here is fine, the calculation is correct, but the answer over here is incorrect, okay? I accidentally moved my decimal place in the wrong direction. If I choose to write it based on my calculator is appearing this particular value, okay? But if I wish to shift it to times 10 to the power negative 6, it should be 66.7 times 10 to the power negative 6 farad. But it happens that I shift the decimal place to the wrong direction, causing this answer to appear, which is incorrect. Okay, so it's either you write this or this, okay, for your answer. So this one is incorrect, but luckily I usually like to substitute things in terms of fractions, so I also keep the answer in fraction, and when I substitute, luckily I choose to substitute the fraction, so the answer here is still correct. So there's no issue with my calculation of time constant. It's just that I write my final answer for effective capacitance to be incorrect. Okay, so just this one is a mistake, but I don't think it will contribute anything because I do my substitution correctly to determine my time constant, and my substitution here is correct. I don't think this answer has marks for this, but in this case, this is my mistake lah. It's me moving my decimal place wrongly. Okay, so I think these are the two mistakes that I make for this particular PSPM set. Definitely should reduce my current mistake, but that's it for now. Thank you very much.